We choose to go to the moon in this decade and do the other things, not because they are easy, but because they are hard.
Godspeed, John Glenn.
Roger, 0G, and I feel fine.
I feel the liftoff. The clock has started.
This is a new and strange environment at first. Just suddenly finding yourself in orbit.
Okay, I'm separating from the spacecraft. Getting my feet out. Okay, I'm out. Really looks funny out there in my glove out there, Jim.
Jimmy 4, get back in.
Okay.
Liftoff. We have a liftoff. 32 minutes past the hour. Liftoff on Apollo 11.
Houston, Tranquility Base here. The Eagle has landed.
Hello and welcome. This is Michael Annis, and you're listening to episode 48 of the Space Rocket History Podcast. I recommend listening to episode 47 before you listen to this episode. And now, Gemini Design, 1961. 1959 and 60 saw their fair share of false starts, dashed hopes, and aborted plans. But in 1961, NASA's manned spaceflight program altered course. Within months after taking office, President Kennedy and his advisors found compelling reasons to support an American manned spaceflight program far larger than Project Mercury. At the policy-making level in headquarters, thinking shifted from lunar reconnaissance to lunar landing. This change was crucial not only for the lunar program itself, but also for what was to become Project Gemini. Before 1961 was over, that shift would provide justification for a rendezvous development program. In the field, the newly independent Space Task Group stopped talking about an improved Mercury capsule and began working on it. Plans for a lunar landing mission and work on an advanced Mercury proceeded through the summer of 1961 at different levels and varying rates. These separate paths converged in the autumn to give birth to the Gemini program. Here are some key events relating to Gemini in 1961. In January, NASA's Space Exploration Program Council met in Washington to discuss manned lunar landing. Among the results of the meeting was an agreement that NASA should plan an Earth orbital rendezvous program independent of, although contributing to, the manned lunar program. In February, Space Task Group Director Robert Gilruth assigned James A. Chamberlin, Chief Space Task Group Engineering Division, to institute studies with McDonnell on improving Mercury for future manned space flight programs. Work on several versions of the spacecraft, ranging from minor modifications to radical redesign, got underway immediately. Early in March, the prospect of conducting extravehicular operations prompted Max A. Faget of Space Task Group to query John Yardley of McDonnell about the possibility of a two-man version of the improved Mercury. A design drawing of the two-man Mercury was then prepared. In April, NASA issued a study contract to McDonnell for improvements of the Mercury spacecraft. A key result of the study was the idea of changing the equipment location from inside the pressure vessel, where it had been in Mercury, to outside the pressure vessel. On May 1st, anticipating the expanded scope of manned spaceflight programs, Space Task Group proposed a Manned Spacecraft Development Center. The nucleus for the center existed in the Space Task Group, which was handling the Mercury program. A program of much larger magnitude would require a substantial expansion of staff and facilities and of organizational and management controls. This would eventually grow into the Manned Spacecraft Center in Houston. On May 8th, Martin Company personnel briefed NASA officials in Washington, D.C. on the Titan II weapons system. The Martin Company proposed using the Titan II as a launch vehicle for a lunar landing program. NASA was not willing to commit the Titan II for a lunar landing, but Mercury engineering manager James Chamberlin believed Titan II would work well for the improved Mercury. Weight was the most serious constraint in spacecraft design. An improved Mercury meant a heavier Mercury, since the price for packaged components was extra kilograms. This in turn meant that the new design called for a launcher more powerful than Atlas. Titan II had power to spare, its total thrust being almost 2.5 times that of Atlas. Not only could it easily lift the heavier spacecraft, but it could also carry the redundant systems that would make it a safer booster for manned space flight. Titan II ran on storable hypergolic propellants. Hypergolic propellants burned simultaneously on contact. This meant that Titan II did not need an ignition system. Both fuel and oxidizer could be stored and used at normal temperatures without the need for cold storage or handling facilities, unlike Atlas, which required super cold for the liquid oxygen. The Titan II's fuel used a blend of hydrazine and unsymmetrical dimethyl as a fuel with nitrogen tetroxide as an oxidizer. Furthermore, the lessons learned from Titan I enabled the reduction of 172 relays, umbilicals, valves, and regulators in the first version of the missile to only 27 in Titan II. This simplification struck a responsive chord in Chamberlin, who saw in it something to match what he had been trying to achieve in redesigning the Mercury capsule. Booster and spacecraft seemed almost to have been made for each other. Titan II's self-igniting propellants had yet another advantage. They reacted much less violently with each other than did the cryogenic propellants of Atlas. In May 1961, there was still some question about whether a Titan II explosion would be sufficiently less violent compared to Atlas to permit the use of an ejection seat in the capsule. Ejection seats not only promised to relieve a major source of trouble by getting rid of the escape tower, they also furthered the concept of modularization, keeping each spacecraft system as far as possible independent. The paramount objective in the program, according to Chamberlin, was to disassociate systems. Ejection seats, in what Chamberlin called, quote, a very happy coincidence that was fully realized at the time, end quote, also fitted in nicely with another design change, substituting a paraglider for a parachute recovery. Still, in May of 1961, Chamberlin was not ready to commit to using Titan II, but that's the way he was thinking, and his active distaste for escape towers made him eager to include ejection seats in his design. Moving on to May 25th, in a speech to Congress on urgent national needs, President Kennedy committed the U.S. to landing an American on the moon before the end of the decade. The metamorphosis of the Space Task Group into the Manned Spacecraft Center and its move from Virginia to Texas followed directly from this decision. Space Task Group had been created solely to manage Project Mercury. As a single-purpose task force, it was outmoded. Project Mercury now became only the first step on the path that was to lead Americans to the moon before 1970. In early June, the Space Task Group issued 3 contracts for a design of a manned spacecraft paraglide landing system. The purpose of the study was to define and evaluate problem areas and to establish the design parameters of a system to provide spacecraft maneuverability and controlled energy descent and landing by aerodynamic lift. On July 7th, Walter Burke of McDonnell summarized the company's studies of the redesigned Mercury spacecraft using 3 possible configurations. First, the minimum change capsule, modified only to improve accessibility and handling, with an adapter added to carry such items as extra batteries. Second, a reconfigured capsule with an ejection seat installed and most of the equipment exterior to the pressure vessel on highly accessible pallets. And third, a two-man capsule, similar to the reconfigured capsule except for the modifications required for two rather than one-man operation. The capsule would be brought down on two Mercury-type main parachutes. The ejection seat served as a redundant system. NASA decided McDonnell was to concentrate all its efforts on two versions of the advanced spacecraft. The first required minimum changes. It was to be capable of sustaining one man in space for 18 orbits. And the second, a two-man version of the capsule, capable of advanced missions that would require more radical modifications. The latter part of July was dominated by two engineering proposals. The first was from James Decker of the Martin Company. He proposed a Titan-boosted Mercury vehicle. His proposal outlined a Mercury Titan program expected to span an 18-month flight schedule. The program would benefit from the Air Force's Titan II booster development and test of the ballistic missile system and the considerable design and test that the Air Force had expended in the Dyna-Soar program to adapt the vehicle to manned spaceflight. This would be a significant cost savings since the Air Force was paying for the design and the development. Another proposal came from the Space Task Group engineers Chamberlin and Rose. Their proposal was a little more radical. They wanted to adapt the improved Mercury capsule to a 35,000-pound payload, including a 5,000-pound lunar lander. This payload would be launched by a Saturn C-3 in the lunar orbit rendezvous mode. You will definitely want to see the drawing of this one-man lunar lander. Of course, this proposal was in direct competition with the Apollo proposals that favored direct landing on the moon with a 150,000-pound payload launched by a Nova-class vehicle with approximately 12 million pounds of thrust. In October of 1961, things began to get more serious. Concepts, ideas, designs, and proposals began to congeal, and a plan of action was formed. The Space Task Group prepared a project summary presenting a program of manned spaceflight for 1963 through 1965. A two-man version of the Mercury spacecraft would be lifted by a modified Titan II booster. The Atlas-Agena-B combination would be used to place the Agena-B into orbit as the target vehicle for rendezvous. The proposed plan was based on an extensive use of Mercury technology and components for the spacecraft. A project office would be established to plan, direct, and supervise the program. Manpower requirements for this office were expected to reach 177 by the end of fiscal year 1962. Estimated cost of the proposed program was about $530 million. The Space Task Group justified this plan by suggesting that the next step in manned space exploration after Mercury would be to gain experience in long-duration and rendezvous missions. The Mark II program was to provide an immediate continuation of a successful Project Mercury using equipment and vehicles already developed for other programs as much as possible. The Mark II would allow a much wider range of mission objectives than Mercury, which could not readily be adapted to other than simple orbital missions of up to 1 day's duration. Mark II objectives encompass flights of longer duration than the 18 orbits to which Mercury was limited, making a multi-man crew necessary. Mark II would contribute to the development of operational techniques and equipment for extended space flights and provide data on psychological and physiological effects on the crew of lengthy periods in the space environment. Objectives also included flights to develop techniques for achieving rendezvous in orbit, a necessary prelude to advanced flights in order to extend the limits on missions' capabilities imposed by the limitations of available boosters, and provide a controlled landing to avoid or minimize the magnitude of the effort required to recover spacecraft at sea and to put spacecraft on something like a routine basis. The Mark II project would be quickly accomplished. Not only would most hardware be modifications of what already existed, but equipment would be modularized, allowing mission requirements and available hardware to be maintained in a balance with minimal dislocations. 12 flights were planned, beginning with an unmanned qualification flight in May of 1963. Succeeding flights would occur at 2-month intervals ending in March of 1965. Flight number 2 would be a manned 18-orbit mission with the twin objectives of testing crew performance in missions of that length and of further qualifying the spacecraft for longer missions. The next 2 flights, 3 and 4, would be long-duration tests to demonstrate the crew's ability to function in space for up to 14 days. Remaining flights were to establish orbital rendezvous techniques and to demonstrate the capability to rendezvous and dock in space. At last, we had a workable plan. Final approval for the Mercury Mark II program was given on December 7th. On December 11th, NASA laid down guidelines for the development of the 2-man spacecraft. The 2-man spacecraft would retain the general aerodynamic shape and basic system concepts of the Mercury spacecraft, but would also include several important changes. Increased size to accommodate 2 astronauts, ejection seats instead of an escape tower, an adapter ring that contained special equipment not needed for re-entry and landing that could be left in orbit. Housing of most systems hardware was outside the pressurized compartment for ease of access. Modular system design was used rather than integrated. Spacecraft systems for orbital maneuvering and docking and a system for controlled landing was added. Target date for completing the program was October 1965. This is how Gemini project manager James Chamberlin justified the changes made from the Mercury capsule.
The main trouble with the Mercury capsule was that most system components were in the pilot's cabin. And often, to pack them in this very confined space, they had to be stacked like a layer cake, and components of one system had to be scattered about the craft to use all available space. This arrangement generated a maze of interconnecting wires, tubing, and mechanical linkages. To replace one malfunctioning system, other systems had to be disturbed. And then, after the trouble had been corrected, the systems that had been disturbed as well as the malfunctioning system had to be checked out again. In Gemini, systems are modularized and all pieces of each system are in compact packages. The packages are so arranged that any system can be removed without tampering with any other system, and most of the packages ride on the outside walls of the pressurized cabin for easy access. This arrangement allows many technicians to work on different systems simultaneously.
Another troublesome problem with Mercury was the sequencing system. Chamberlin argued that one of his chief motives for keeping systems modular was the endless complications Mercury experienced because so many sequentially controlled operations were built into it. Most of Mercury's flight operations could be controlled by the pilot, but safety demanded that they also be automatic. Each complex series of events triggered by an appropriate signal and ordered through a predetermined sequence by a tangle of electrical circuitry. Mercury's sequencing was so complex that Chamberlin recalled it as, quote, the root of all evil, and anybody that really worked on Mercury, that's all they talked about, end quote. The new design relied on pilot control instead of merely allowing it and backing it up with automatic sequencing. The result was a much simpler machine. The 220 relays in Mercury, for example, were reduced to 60 in Mercury Mark II. Another change, removing the escape tower and installing ejection seats, eliminated the most complex sequencing problem of all. Mercury's escape tower used a rocket to pull the capsule away from the booster in an emergency during or just after liftoff. The escape tower added hundreds of kilograms to the capsule's weight, even though it was essentially irrelevant to the function of the capsule itself. In a successful flight, it was jettisoned shortly after launch. Yet it had many relays and complex wiring that made it inherently untrustworthy, and it required extended checkout time. Another significant improvement over Mercury was an enlarged overhead mechanical hatch, which would allow the pilots to get in the spacecraft more easily and to get out more quickly in an emergency. It was another way of making the new spacecraft a truly operational machine, one that could be entered and left like an airplane. Such a hatch was also required if ejection seats were to be used. But it also had a special virtue that its designers were well aware of, though they did not talk about it. A large mechanical hatch would enable the pilot to leave and return to the spacecraft while it was in orbit, and thus permit extravehicular activity. The last key event of 1961 occurred on December 26th. On that date, the Manned Spacecraft Center directed the Air Force Space Systems Division to authorize contractors to begin the work necessary to use the Titan II in the Mercury Mark II program. The physical work on Gemini had begun. Thanks for listening to this archive episode of the Space Rocket History Podcast. If you are financially able, please support the podcast by going to the homepage, spacerockethistory.com, and clicking on the orange Donate button or the Patreon link. Thanks.